quick video with some notes to help you study before you take the Chapter 2 test in statistics. So the first question says that if you have an outlier, how will the outlier appear in a histogram? Well, a histogram is a set of different bars that show how frequently different values happen. So if there's an outlier that's a very different amount than the other values of data, then it will be a bar that will be far from the other bars of the histogram. And since it says there's only one outlier, then it'll have a frequency of 1. Now we get an example to actually try to create a histogram. So the most common value is 6.2 through 6.249, so that one should be the highest. And it looks like that one could be number C or number A. However, C is the only choice because the frequency from 6 to 6.049 is 3, and this matches up with 3. That one does not, and that one also does not. So C is the only choice that works. So it says, does the histogram appear to depict data that have a normal distribution? Well, it looks kind of like a bell-shaped curve. So the frequencies generally increase to a maximum and then decrease, and it's roughly symmetric, somewhat close to the same size on both sides of the histogram. So let's see. I would go with answer A. There we go. The last digits of the heights of 60 statistics students, the last digit of the heights, were obtained. So the most common one is 5. So 5 should be, actually 0 is the most common one. So, and then 5. So 0 should be the highest, and then 5 should be close. So it could be, and it should be 16 for 0, so it could be A, or it could be D. Now, according to D, 6, 7, 8, 9 are all exactly the same. According to A, 6 and 7 are the same. 8 is slightly higher and 9 is slightly lower. So therefore it must be A. Are the data reported or measured? So it seems like they're probably reported, and the reason for that is, why are there so many people whose height is like exactly 5'0" or 6'0", or let's say 5'5" or 6'5"? So they don't appear to be measured because the data would probably have a bigger variety of values instead of so many 0s and 5s if they were actually measured. So they appear to be reported because the certain heights occur a disproportionate number of times. So construct a stem and leaf plot of the test score is 67. So 6 would have a 7 after it. 7 would have a 3 after it. Let's see. And a 5, because there's also 75. 8 would have a, so let's see, it could be, so for A, no, it could be, the only ones it could be are either C or D. So 8 should have a 5, no, yeah, 5, a 9, 9, and a 7, because there's an 87. So D is the only choice that works with everything so far. It has a 67, a 73, 75, an 85, an 87, an 89, another 89. And then it also even has a 90, a 98, and a 100. So D is the correct one. And it says, now if you look at this sideways, this 7's kind of like a short little horizontal bar. This is like a little bit taller of a bar. This is like a taller bar, then it gets shorter and then even shorter. So if you look across the top of it, see it kind of curves up and then down. That's just like a histogram. So the lengths of the rows are similar to the heights of bars in a histogram. Longer rows of data correspond to higher frequencies. So that's the best answer. Okay, now here's some time series data of movie theaters. Now notice mostly the overall trend is going up. There's a couple times when it goes down just a bit, but mostly it goes up, although it somehow levels off slightly at the end, and it also has a tiny dip near the beginning. So we would expect to see a graph that has a tiny dip near the beginning, like this one, and then it goes up and kind of levels off near the end. So let me look at the data again. Yes, it goes to 36 and back up again and then a little tiny bit down. Okay, so I would go with B. What is the trend? Well, the trend is upward, so upward. But this is the drive-in movie theaters, which have a downward trend. So there appears to be an upward trend, which is unlike the drive-in movie theaters, which have a downward trend. So let's see here. In a study of retractions of biomedical journals, 400 were due to error. 821 were due to fraud. So fraud happens the most often. So it could be this one or this one. And then 400 were due to error. So 400 could be that one. The red one looks like it's higher than 300, so it could be 400. And then duplication, 317, that looks about right, just slightly above 300. Then 254 had other issues. So that looks about right. And then 188 were due to plagiarism. So that's the shortest. Okay, perfect. So I would go with B. Among such retractions does misconduct, fraud, duplication, and plagiarism appear to be a major factor? Well, yes, because there's tons of fraud, tons of duplications, and tons of plagiarism. There's only 400 that were actually due to error, but more than twice that much that were due to fraud. So I would say yes, misconduct appears to be a major factor because the majority of retractions were due to misconduct. So I'd go with that one. Then question 7. So this one says, a study was conducted just to determine how people get jobs. Most of the people got jobs from help wanted ads. So that would be the biggest amount. And then next most is networking. So then, so this is kind of hard to see because it's so small. Let's see. So help wanted is definitely the biggest. Networking, which should be the next biggest. So wait, it can't be that one, right? Because in this one, networking is not the second biggest. So we can, this first choice is wrong. Okay, then how about the second choice? That one, help wanted ads is the biggest as well. And in this one, now, whoops, in this one, networking is not the second biggest. So how about this one? Okay, so this third one, help wanted is the largest. And then the light blue one, networking, is the second biggest. And then executive search term firms, the red one is the next bit largest, and then mass mailing is the smallest. So that's the correct one. And which one's more effective? Well, the Pareto chart is much more effective because look how hard it was to figure out which one was the largest. Where if you look at the Pareto chart over here, it's super easy to see that presto, you can see instantly help wanted is the most frequent, then networking, and then executive search firms, and then mass mailing. So the Pareto chart is more effective at helping you understand the data. All right, so the first one should be at 99, and then the highest one, 855, that should be the, let's just see. Okay, that should be, there should be 4 points, 1, 2, 3, 4, 1, 2. So it can't be, let's see. Let's just see here. So let's just see. So age 45 to 64. So 99, 116, 794, 647. Okay, let's see here. So 8, the highest point should be at about close to 900. So it could be that one or that one. It can't be that one because this one increases too fast. So I'm going to go with this one. And then notice the reason I went with that one is because the first two groups of numbers are fairly low, like this. And then the next two are, so let's see, 99, 116, 855, 590. And then it goes down back again. Okay, so that's the one I'm going to go with. And then it appears to be skewed to the left because the left side is kind of a lower tail out on the left side. So it appears to be skewed to the left or negatively skewed. So this looks like the men have a salary that looks more than double of women. According to this graph, it looks that way. Now, if you look at the numbers, you can tell that it's not. But the height of this blue bar is more than twice the height of the red bar. So this graph creates the impression that men have salaries that are more than twice the salaries of women. And aside from the question about salaries being too high or not, the graph, if a graph does not show the true 0 point on the graph, then it is an unfair comparison because the vertical scale doesn't actually start at a true 0 point. So does the graph depict the data fairly? The answer is no, because the vertical scale in this graph doesn't start at 0. So a more fair comparison of the data would be the one that actually starts at a true 0 value, which would be this one, and it still shows the salaries of, no, wait, it still shows, okay, just 1 second. So according to this, women have a salary a tiny bit less than 60,000. Let's see. So, okay, that one doesn't start at 0 though. So the closest choice is, it looks like this one starts at exactly 60,000, and this one starts a little bit below, but this one is the wrong choice because it doesn't start at 0. So apparently I just can't see close enough to see this one must actually start a tiny bit under 60,000. But the scale is a lot smaller since it starts at 0. So this one would be the one that shows the same exact information comparing women to men, but it starts at 0. And so there we go. Okay, in this section we use R to denote the value of the linear correlation coefficient. And the reason that it's called linear, it refers to a straight line. And R measures how well a scatter plot fits a straight line pattern. All right. Okay, what is a scatter plot? It's a graph of the data points in pairs x and y. So it's a graph of paired data. So it could be A or D. Oh, and it has to be quantitative data. It's a graph of paired quantitative data. It provides a visual image of the data plotted as points, which helps show any patterns in the data. So that's that. So let's try to actually do a scatter plot. So here is some data. All right, so notice that, let's see, what is the lowest value of the president's height? 168. And the highest president's height is 195. So 168 through 195, and at 168, the opponent was 186. So on the left side, it should have a somewhat high value on the graph, and then on the right side, it should have a somewhat medium value. So let's move this so we can see the graphs at the same time. So on the left side, it has a somewhat high value. So it could be this one. On the right side, it has a somewhat medium value, so it couldn't be that one. So it's either D or B. And now what's the highest value of the opponent's height? Let's see, 195. 195. Okay, so 183, when x equals 183, the opponent's height is 195. So at 183, it should have the highest point. What about the lowest point of the opponent? So the lowest opponent's height was 169. So let's see, and that happened at 191. So I think this is really hard to figure out. There's so many really close data points. So one thing you can do is you can click on this button that says Open in StatCrunch, and you can actually make a scatter plot. So the x variable is the president's height, the y variable is the opponent's height. So let's just actually make a graph. Now, this StatCrunch software is super cool, and you're going to be using this in other chapters. So now we can see an actual graph, and you can use this right during your test. And now we can see for sure that, let me close this data. So it was hard to guess just by guessing by hand, but now we can see the pattern exactly. So do you see how there are 3 points near the end, boom, 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 like that? And those same 3 points right here, chuk, 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 there they are. Now let's see if those points are on this one. No, on B, which is the only other possibility, they're not those 3 points exactly like that. So D is the only graph that shows the same thing as the actual scatter plot. So D is the only right answer. Now, does that look like a straight line? No, this one looks somewhat like a straight line. This one looks kind of like a straight line, but D does not. So the answer of a correlation is no. There does not appear to be a correlation because there's no general pattern to the data. So how tall you are as president doesn't necessarily relate to how tall somebody is who's running against you. Okay, so this shows the pounds and highway mileage for 7 automobiles. Okay, so the weight is the x value, so as the weight gets higher, the miles per gallon tends to go down. For example, this one is 21, so there's only one graph that shows that when the weight is higher, like 4,000 pounds, that the miles per gallon is going downwards. So B is the only one that shows the miles per gallon going downwards as the weight goes upwards. So the weight on the x-axis is getting higher, the miles per gallon is going lower. Is there a linear relationship? Well, so far there appears to be. So yes, as the weight increases, the highway mileage decreases. Okay, so this one says there were 8 bears that were measured. So if there's 8 that were measured, then the critical value of R is 0.707. So, and it's also negative or positive. So negative 0.707, positive 0.707. Negative 0.707, positive 0.707. So the correlation given is 0.701. So is 0.701 between those values? 8. Okay, so let's see. 0.701, yes. 0.701 is a little bit less than 0.707. So it is between the critical values. So there is not sufficient evidence to support the claim of a linear correlation. Now let's try this one. So a p-value indicates the probability of a linear correlation coefficient that is at least as extreme as the one that you got. And that value, and that p-value is 0.633, which converts to 63.3%. 63.3%, which is high. Normally, anything above 5% is considered a high p-value. So if there's a high p-value, there's not enough evidence. There is not sufficient evidence to conclude that there is a correlation. And now this one, the p-value is 0.028. So the probability of a linear correlation coefficient that is at least as extreme is 2.8%, which is, that is less than 5%, and so that one is classified as low. So there is sufficient evidence to conclude that there is linear correlation between weight and highway fuel consumption. So there we go. All right, those are some notes to help you as you take the Chapter 2 test.